Thank you very much, Rachel, and welcome to my talk, JavaScript Engines, the Good Parts. Initially, I was going to give this talk together with Brian Tolson from Microsoft. You know, nice guy, blonde hair, working on a JavaScript VM. But yeah, then life happened, and now I'm standing here alone.
What are you talking about? I'm right here, man.
Yeah, I'm right here. I'm Brian. What's up, guys?
This is weird.
Yeah, now we have two Brian lookalikes. I think I cannot do a talk with both of you, sorry.
Okay, so thank you, Peter, for the cameo.
You guys got this. Okay, thank you.
Applause for Peter. All right, so with that out of the way, let's get started with the actual presentation, JavaScript Engines, the good parts. Nowadays, JavaScript runs not only in web browsers, but also in Node.js, in React Native, in Electron. It even runs on IoT devices, and I've recently been told it even runs in space. So there's that. JavaScript is everywhere nowadays. As a developer, learning JavaScript or improving your JavaScript skills is an excellent time investment. So let's take a look today behind the scenes of how JavaScript engines work. This is V8. It's the JavaScript engine used in Google Chrome, Node.js, and Electron, for example. And recently, we've been speaking and writing a lot about how V8 works behind the scenes. However, it's not just V8 out there. There are more JavaScript engines out there. So we're going to do a little bit different today.
Yeah, actually, we're going to look at some of the fundamentals that are common to all the JavaScript engines out there. And these fundamentals make it possible to write these amazing JavaScript applications that we see today and of which we heard a lot at this conference already. So starting with that, it's not just V8, there's also an engine called SpiderMonkey, which is the JavaScript engine that powers Firefox. And fun fact, there's even a Node fork using SpiderMonkey, which is called SpiderNode.
I really like that name, SpiderNode. Then there's Microsoft's JavaScript engine, which they use in Edge. It's called Chakra. And the main part of the Chakra engine is open sourced as ChakraCore. There is a Node ChakraCore project, which is basically a Node.js flavor powered by ChakraCore instead of V8.
And that's not all. There's also JSC, or JavaScript Core, which is the engine that was initially built for WebKit and is nowadays powering Safari, but also React Native applications.
So these are the major JavaScript engines out there. And if you want to play around with any of these engines directly, which is without going through an embedder like a browser or Node.js, then you can install this tool called JSVU. So you install it using npm, you install it globally, you follow the README instructions, and after that, you can basically just run V8, SpiderMonkey, Chakra, JSC straight from the command line. And the JavaScript you run in there will run directly in the engine itself. OK, so now that you have all these JavaScript engines installed on your system, let's take a look what they all have in common. It all starts with the JavaScript code that you write. So the JavaScript engine parses the source and turns it into an abstract syntax tree, or AST. And this AST gets fed into the interpreter, which can then start to do its thing, which is to produce bytecode. And this is pretty cool, because at this point, the engine is running your JavaScript code. However, to make it run more smoothly and more efficiently, there's also an optimizing compiler pipeline. So the bytecode gets fed into the optimizing compiler alongside profiling data that we collect while the code is running. And that way, the optimizing compiler can make some assumptions based on the profiling data and generate highly optimized machine code that runs more efficiently. And if one of those assumptions turns out to be incorrect later, it's no big deal, because we can just de-optimize and fall back to the bytecode from the interpreter. So let's focus on the important part here, which is the part where the code actually gets run. So each JavaScript engine has some kind of pipeline with an interpreter and an optimizing compiler pipeline. The interpreter generates bytecode, and the optimizing compiler generates highly optimized machine code.
Wait, you just stole my punchline. This was the V8 slide. So actually, that's exactly how V8 works. Our interpreter is named Ignition, and the interpreter is responsible for generating and executing the bytecode. And as it's executing the bytecode, it collects profiling data. And when a function gets hot, so let's say you call it a couple of times, then we feed it to Turbofan, which is our optimizing compiler. And that uses this profiling data to generate highly optimized machine code.
I love hot functions. SpiderMonkey does it a little bit differently. They have not one, but two optimizing compilers. So the interpreter optimizes into the baseline compiler, which produces somewhat optimized code. And combined with profiling data that it gathers while that somewhat optimized code is running, it gets fed into the IronMonkey optimizing compiler, which produces more highly optimized machine code.
And you did it again. So this is exactly ChakraCore, except that they have different names. So in ChakraCore, the first optimizing compiler is not named baseline, but simple JIT, where JIT stands for just-in-time compiler. And it generates somewhat optimized code. However, when a function gets really hot, then it feeds it to full JIT, and that generates really awesome code out of this.
And then there's JSC, which takes it to the extreme with not one, not two, but three optimizing compilers. So it all starts with LLint, the low-level interpreter, which produces the bytecode. And from there, they can optimize into the baseline compiler, which produces somewhat optimized code. But from this baseline compiler, based on some heuristics, they can either optimize into the DFG compiler or the FTL compiler. So let's look at what else all these JavaScript engines have in common by zooming in on some aspects and how they implement them in common. Because besides these differences that we just discussed at a very high level, all engines follow the same architecture. They have some kind of parser and then an interpreter and compiler pipeline. For example, how do JavaScript engines implement the JavaScript object model? And which tricks do they use to speed up accessing properties on objects? As it turns out, all major engines implement this more or less similarly.
Wait, but Matthias, isn't it the case that all objects in JavaScript are just dictionaries?
Right, that's true. If you look at the JavaScript spec, it turns out that objects are actually dictionaries with string keys. And the string keys map to not just the value, but to something that the spec calls property attributes. So in this example, the X and the Y are string keys in a dictionary, according to the spec. And the 5 and 6 values are just values within the property attributes for that property. So other than the value, property attributes can also store whether the property is writable, enumerable, and configurable. And this is not something that JavaScript engines make up. It's part of the ECMAScript spec. Writable determines whether the property can be reassigned to. Enumerable means that the property can show up in for-in loops. And configurable means that it's a deletable property. And you can actually get to these property attributes in JavaScript for any object and any property by using the object.getOwnProperty descriptor API.
Interesting. So that's how JavaScript sees objects. But what if we take arrays?
Well, you can think of arrays as a special case of objects, really. There's only a couple of differences. One difference is that arrays have special handling for array indices.
Wait, what's an array index?
An array index is a spec term. Basically, arrays are limited to 2 to the power of 32 minus 1 items. So that's the maximum array length you can have. So an array index is just any valid integer within that range from 0 to 2 to the power of 32 minus 2.
OK, so not every integer is a valid array index.
Exactly.
Got it.
Yeah.
OK. So you mentioned more differences?
Oh, yeah. Another difference is the magical length property that arrays have.
Wait. Magic?
It is pure magic. Like, if you look at this example, the array has a length of 2 in the beginning. And then we add another item to the array, and automatically the length property is updated. The JavaScript spec defines how this works, and JavaScript engines have to do this automatically in the background. As a JavaScript developer, you don't have to go and manually update it. So let's take a look at how JavaScript defines arrays. They're stored similarly to objects. For example, all the keys, including the array indexes, are represented as strings explicitly. So the first element in your array will be the string key 0. And the length property is just another property that happens to be non-enumerable and non-configurable. Once an element is added to the array, JavaScript automatically updates the value property attributes for this property, for the length property.
OK, that looks really similar to the objects, indeed, yeah. So now we know how objects are defined in JavaScript. And one observation is that many programs mostly operate on objects. And the most common operation in these programs is actually the property access. So
seems like a common thing to do.
I guess we better make that fast, right? And in fact, what we see in the wild is that most objects in the same program tend to have the same property keys. At least there is a set of objects that have the same. So you could say that all of them have the same shape.
Right. That makes sense. It's also very common to access the same property on different objects that have the same shape. So with that in mind, JavaScript engines can optimize object property access based on these shapes. So let's take a look at how that works.
Okay, let's assume we have this one object here, which has properties x and y, and it's represented using this dictionary data structure that we saw before. So the x and y are stored as strings in the dictionary and point to the property attributes for these individual properties. So if you then write something like object.y in your program, the engine has to reach out to the JS object, find the key inside of it, reach out to the property attributes, and eventually load the value from it.
Okay, so where are these property attributes stored? Do we store them as part of the JS object data structure itself? Because that seems a little wasteful based on what you just said. If we expect more properties, well, more objects to have the same shape, then you would end up duplicating all that information for every single object. That seems wasteful memory-wise.
That's a good observation. And I think some people made this observation already. At least this is kind of how we represent it in JavaScript engines nowadays. So what we do is that the engine stores the shape separately from the values of the attributes. So like in this case, the shape describes which properties you have and which property attributes you have on this, except for the value. So instead, the property information contains the offset where you find the value inside of the JS object, the offset where you find the value. And it totally makes sense when you start to look at multiple objects that have the same shape. So now you only need one instance of this shape, and the objects only contain the information that is unique to this object. So you don't repeat this information that is common anyways.
So even if we have a million objects, there will only be one shape, as they all have the same shape, and they will all point to the same one.
That's true.
It seems like it would save a lot of memory.
I hope so, yeah. And this is not even something that JavaScript engines made up. This had been there before. So like, there's been a lot of research on this. And if you look at academic papers, then they're often not called shapes, but hidden classes.
Ooh, that would be a confusing name in a JavaScript engine, because classes are already a thing in JavaScript.
Wait, you find that confusing? You know that V8 calls them maps?
Oh, that's the same problem. It's a terrible name.
Okay, how about types for ChakraCore?
That's not confusing at all.
Okay, I can offer structure for JSC.
I like the name structure. That kind of makes sense. But I'm going to keep calling them shapes, because that's what SpiderMonkey calls them, and I like the name. So Benedikt, it seems like it's a common thing to, if you have an object, to then add a property to it. So what if you have an object with a certain shape, you add a property to it, how does the JavaScript engine find the new shape?
So what JavaScript engines do is that the shapes inside of the engine form so-called transition chains. So let me run you through this example quickly. Let's assume we start with the empty object. So this object initially points to the empty shape that doesn't have any property on this. Okay, so now you start adding a property to it. Like in our case, we add x, which means we transition to a new shape that has the property x on it with the property information, and we append the value for this property to the object. And then we record inside of the shape, inside of the property information, that this value can be found at offset 0 now. So let's say we add yet another property to it, like in this case y. Then we do the same as before. We introduce a new shape that contains this new property in addition to the x property, and we append the value to the object. And we record that the value can now be found at offset 1. However, if we do this, then we might waste a lot of space because we repeat the full table all the time, plus the new thing that is added.
Right, we're repeating x, like all the information for x is duplicated.
All the information for x is duplicated. So that's not really what engines do. Instead, what you do is you just remember the information about the new property that was added.
Right,
and
we don't have to repeat the information for x because we can just find it earlier in the chain.
That's exactly the trick. So we introduce a backlink to the previous shape so that you can just walk the transition chain backwards until you find the shape that introduces the property, and then you know where to look into the object. So just looking at this example, if you now need to find x on it, you would start at the last shape and it'd see, okay, this is not the one I'm looking for because it introduces y. Then you walk back once and, oh god, there's x, awesome. Now I know where to find it.
So that's what happens when you type o.x in JavaScript. Now I know. So what if you have two objects with the same shape, and then you add a different property to each of them? That way you cannot really chain these shapes, right?
There's no way to chain, no. But what we do instead is we introduce so-called transition trees. and we branch off in various ways from shapes. So let's look at this example. This is what we learned before already. So we have the empty object, we introduce X on it, which means we introduce two shapes and a single chain from the empty shape to the shape that contains X. Now, if we run the second line of code, if we start again with an empty object and we add a property Y to it, then we branch off the empty shape with the property Y, and we end up with a tree that contains a total of 3 shapes in 2 chains.
Right. So does that mean if we walk up the shape tree, we always end up at the empty shape?
No, not necessarily. There's always an exception to the rule. And the reason is that JavaScript engines have special treatment for object literals that already introduce properties from the get-go. So like in this case, the first thing is what we saw before. We start with the empty object, and then we add X to it. And the second line is we start with an object that already contains X. And you can imagine that it might be a bit faster to just construct objects with the properties on it already. So what we end up with, for example, in V8 and in SpiderMonkey, is this is the first case that we know. So here we start from the empty object, and we add X to it later, which is exactly what we had before. But now, the second example, we start with an object that already contains X from the beginning. So we introduce a new root shape that already contains this X, and we don't branch it off the empty shape.
Right,
and
so we can just skip over that empty shape altogether in this case.
That's true.
Nice.
And the reason why we do this is to keep the transition chains short, because otherwise it's a lot of metadata that we waste, and also because it's more efficient to construct objects this way.
This sounds super familiar. Didn't you write a blog post about exactly this?
Shameless plug, yes, I did. So I actually published a blog post last year about this, where I tried to highlight how these subtleties with the shapes can have effects on real-world performance, especially for common patterns found in React applications.
I read that blog post, and it talks a lot about this thing called ICs. What are those?
That's actually the magic inside of the engine. No, it's not.
More magic.
It's more magic. So IC stands for Inline Cache. And the inline caches are the key ingredients that is necessary to make JavaScript run fast. And it's also the main motivation for actually having shapes.
So how do these ICs work exactly?
So JavaScript engines use ICs to memorize information where to find properties on objects, so that we don't need to repeat expensive property lookup on each property access.
OK, so how does that work?
OK, let me run you through this example. So we have a function getX, which takes an object O and loads the property X from it.
That seems like a common thing to do, like get a property somewhere.
Yeah, I think I've seen it in the wild. So if we feed this to JavaScript core, then it generates the following bytecode. So this bytecode contains 2 instructions. The getById instruction, which does the property lookup. In this case, it's getById loads X from arg1, first argument, which is O, and stores the result into log0, and the next instruction just returns whatever is in log0.
OK, this makes sense, but how do ICs come into play here?
So it's not just that. JSC also introduces an inline cache into the bytecode. So in this case, into the getById instruction. This IC contains 2 uninitialized slots initially. And when we now call this function, let's say we call it with an object x:a. As we learned before, this has a shape that contains x. And let's say in this case, the property value for x is found at offset 0. Now we invoke the function with this. What do we need to do? We need to reach out to the shape of this object, search for x inside, load the property information from it, determine the offset, then go back to the object and load whatever is at offset 0.
That sounds like a lot of work.
It is. And since the engine already did this work, it makes a lot of sense to memorize the information that we can reuse on the next call for this function. So let's say we call it, it makes a lot of sense to record this information for the next call. So what we do is we memorize the shape that we have seen and also the offset at which we found x inside of this shape. So when we then call this function again with an object that has the same shape, we only need to check, oh, it's the same shape. Oh, OK, no, it's already offset 0. So I don't need to reach out to the property information at all.
Wow, we can just get rid of that expensive lookup altogether. That sounds great.
Yes, and it's significantly faster.
So how would this work for arrays, where you can expect most elements to be array indices, most properties? So you wouldn't want to store property attributes for each and every array index in each and every array in your code base. That seems wasteful, because you know that they're going to be writable, enumerable,
Definitely.
and configurable.
Yes. Definitely. That would be total waste of space, and metadata would explode.
So what happens instead?
So all engines actually make use of the fact that all array index properties are writable, configurable, enumerable data properties. So let's look at this array. As we know, an array has a property length, which is this magical property, and let's say the length is stored at offset 1 inside of the array. For all the elements that are actually in the array that are indexed by array indices, we store them in a separate elements backing store. And this backing store only stores the values. And it has this implicit tag attached to it, which says that whatever you find in here is writable, enumerable, and configurable.
So we don't have to store any property attributes for array elements?
No.
Because they all match the default.
They are all default values anyways.
But what if someone overrides one of those attributes, though? This is JavaScript. JavaScript is pretty wild.
I know you're wild.
But you can totally do this, though. Like, what if I use object.define property on an array element, and I set one of its attributes to the non-default value of false?
You know, Matthias, whenever you do something like this, you kill a kitten. So, like, just look at this one.
Aww.
You cannot kill it. Impossible. Or you want to kill this one? That would be rude.
So
or, come on.
my heart melts.
Yeah, see.
Oh,
So,
there's a whole bunch of them.
There's a family of kittens, remember? Don't do this. Okay, but kittens aside, so for these edge cases, the engine represents the entire backing store for the elements as a dictionary which map from array indices to full-fledged property attributes. So very much like in the JavaScript specification.
So even if I just use this object.define property on one array index, then the whole array gets stored like this?
Yes,
Oh,
because
yeah.
the basic assumption of the engine is that you don't do this.
Okay.
And also, remember the kittens, come on.
Got it, yeah. I think you're saying that I should avoid using object.define property on array indexes, which is a weird thing to do anyway.
Yes.
Yeah, OK. I guess I won't do that again. So we've learned a lot about JavaScript engine internals today, and we got some actual coding advice out of it as well. So let's recap the main takeaways. Always initialize your object in exactly the same way so that they don't end up having different shapes. And second, don't mess with property attributes of array elements so that they can be stored and operated on efficiently. Think of the kittens. And that's it. Thanks for listening.